All right, so let's go ahead and start. And let me make sure my chat screen is included here. Is it this one? Yeah, okay. Double check. Yep, okay, good. So the topic for the first hour is going to be this. An overview of the reliable data transfer protocol. So this is one of the key functionality in a transport layer service, which is well implemented in TCP. So we'll actually walk through a number of versions of these reliable data transfer protocols or designs. So they're called the RDT in short. All right, so let's start with the overview. We're going to introduce you the need of the RDT and the system we'll be using to describe the RDT mechanism. It's called the finite state machine. All right, 3.4, principles of reliable data transfer. Now, you might see Polly is a little bit more alert talking about this section because this is going to be the most challenging section in chapter 3. And arguably one of the most challenging sections for the entire textbook. All right, so let's talk about reliable data transfer. It's not only challenging, it's also extremely important. All right. So it's not only important at the transport layer, some of the link layer services might also implement some level of reliable data transfer. At the application layer, someone might be using UDP as the underlying transport layer service and implement its own reliable data transfer. So maybe it'll be more efficient than TCP instead of using the native TCP provided in the protocol stack. All right. So it's one of the top problems when one needs to design a communication network. Now this is the setting. We have processes sitting at the application layer. Okay. There's application layer protocol, but there's also transport layer services. These processes depend on to transfer application level messages. So sending processes here, sending out data. Data will go through a channel. Now this is a reliable data transfer service, so the channel is reliable. And hopefully at the other end, the receiving process grabs the data and then interpret the data and things will just work out. Okay. But the thing is, the internet is not exactly reliable, isn't it? So yeah, we do have unreliable channel when packet goes through the internet infrastructure. Now, but application, sending process, receiving process are demanding reliable transfer. So transport layer service here, the sending side and the receiving side each will need to implement some extra mechanism to ensure somehow lost segment is recovered, somehow the flipped bits are corrected. Right? So that is RDT. Okay, and we're going to go through a few generations of these RDTs and show you how the sending side is implemented, how the receiving sides can be implemented such that we provide such a illusion to the application level services. Oh, and by the way, it really depends on how unreliable the channel is underlying. Then the complexity of the reliable data transfer can vary. Very unreliable, very complicated. Not that unreliable, then slightly simpler. Now, we'll be using these notations, RDT send, UDT send, and all these throughout the discussion, introducing you generations of these reliable data transfer protocols. So let me blow it up and explain a little bit further. All right, so sending processes here, generating messages. Those messages get passed down to the transport layer. And those messages are now called data. All right, and RDT send is the function called the sending process calls to pass the data down. Okay. So let me bring it up. RDT send here is to be called from above, from the sending process. okay, and it is to pass the data down such that it will arrive at the receiver end. Good. Well, and these messages is going to be processed here, and a number of these segments will be generated, or packets will be generated. So when we're talking about generally reliable data protocol design, let's just call these packets. Okay, so messages now data, segments is now packet. And the action of pushing the packets down to the unreliable channel is UDT send. Okay, UDT send. So UDT send here is called by the RDT, the protocol sending side, to transfer packets over the unreliable channel. All right. And then, yeah, data is going to travel through the channel and come to the network layer. So that network layer component would call this, okay, RDT receive, to pass the packet further up. So packets gets passed down by calling UDT send. Packets gets passed up, okay, by calling RDT receive. Okay, and this is called from below, from the network layer, when packet arrives. And those packets will be processed here, okay, and then the receiver side of the transport layer protocol is going to call yet another one, receiver data function. So this is called by RDT, the receiver side, to deliver data to the receiving process above. So data here is going to be passed above. So 4 function calls to refer to actions. First, coming from the sending process to the sending RDT. Second, from the sending RDT to the unreliable channel. Third, from the network layer to the receiving RDT. And the fourth, from the receiving RDT back up to the receiving process. Now, we'll try to describe generations of these reliable data transfer protocols. As Polly mentioned slightly earlier, yeah, these various generations, one is simpler, second slightly more complicated, third even more complicated. So they go from simpler RDTs to more complicated RDT. That's because we assume the underlying channel being more reliable to less reliable, to very, very general, like the internet. All right. So that is just to prepare you for the RDTs that we need to introduce coming ahead. Now, another thing that I need to introduce is how I'm going to describe these RDT mechanisms. We're going to use, this thing called the finite state machines. Okay. Finite state machines, FSM. Okay, so here's one state, here's another state, 2 states. So finite number of states. All right, so this is a machine to go from one state to another station, from one state to another state. You might have a transition saying that under this condition, then we go from state 1 to state 2. And in the meantime, we transit from one state to another, we take this action. Right? So the arc here defines when will a machine jump from one state to another, and what is the action to be taken. Okay, hope we're back. Yeah, but it's okay because we're almost done describing the finite state machine. There's just a video, the RDT version 1.0, which is actually very straightforward, assuming that the underlying channel is reliable. So the state machine is very trivial. So we can now go ahead and look at, let's go ahead and look at the video number 2. That is the introduction of RDT 2.0. Where we begin to assume, where we begin to assume that there's going to be bit errors as data travel one way. And now RDT 1.0, the generation number 1. Right? So in this generation, yeah, the assumption is very strong. We're simply assuming that the underlying channel is reliable. As a result, sending side of RDT, receiving side of RDT, there's nothing really needs to be done. So the machine is very simple. So this RDT 1.0 is just so that you are more familiar with the finite state machine notation, right? So underlying channel is perfect. No bit error, no lost packets. Okay, so the sender side of the finite state machine, FSM, will look just like this. Okay, so there is always at least one state that is also the starting state. There's no ending state for these machines because they'll be looping forever. Okay, so starting state is wait for call from above. Okay, so application calling data to be sent to the transport layer. So yeah, calling from application from the sending process is RDT send, isn't it? So when you run into this event, the sender there, yeah, would generate packet out of data. So data is the thing coming from the application. And packet is generated to be pushed out. And to push down, we call UDT send. Right? So this is the FSM at the sender side. Similarly, at the receiver side, call from below. Right, so when that is happening, yeah, RDT receive being called, receiver side of the RDT 1.0 will just extract data out of the packet and deliver the data up to the application layer. All right, so again, events triggering changing of state, and the arc direction indicates which state it changes to. And so a loop coming back is saying that, hey, we stay at the same state. Right? In the meantime, we take these actions. So event triggering the transition. In the meantime, we make the transition take these actions. So you see, sender side keep being triggered from the application, calling this and triggering actions to occur, triggering the state being changed. So that is the general idea of FSM and using it to denote a functioning machine. All right. Sender sends data into the underlying channel. Yeah, here. Receiver sends data from underlying channel. Yeah, here. All right. And then RDT 2.0. So this is when the channel is no longer perfect, but it's not so bad either. We do have some problem, but just this problem, having bit errors, meaning the packets, okay, if you look inside, some of the bits might be flipped. Therefore, it failed passing the checksum at the receiver. So the computed checksum and the packet header checksum somehow didn't match. Receiver then detect bit error. The question is, how do we recover from this error? Well, you know, if you're thinking how to do this in the computer in the transport layer, I'm sure that it's very hard. But if you think this, how do humans recover from errors during conversation? Say, if Polly was trying to describe finite state machine and it sounded really fuzzy to you, what would you do? There you go, right? You type up in the live chat and ask, hey, what do you mean transition? What do you mean changing from state to another state? What do you mean certain event occur and triggering the changing of the state? It's not clear. And Polly then will try to explain again, right? Retransmit the packet again. So, sure, if you abstract this exchange of feedback and data and retransmission, you see the general idea seems to be receiver upon detecting error, sending feedback to the sender. Sender retransmit the packet again, and hopefully the second time it's clear, no longer fuzzy. That is the general idea of RDT 2.0. So to describe RDT 2.0 a bit more formally, those feedback you're providing to me, in the computer system, they'll be either in this form or this form. So acknowledgement there is a positive feedback. Negative acknowledgements, therefore, the negative feedback. Acknowledgements there or acts there are to explicitly telling the sender everything is all right. And next here is to tell the sender, something's wrong, and therefore the sender can retransmit the packet. Okay, so retransmit of the packet is triggered by the receiving of next. This is exactly what's defined in RDT 2.0. So let me stress, there's first, detecting error, second, sending back of the feedback from the receiver, and then retransmission of packet coming from the sender in case negative acknowledgement is received. Now, what's a little bit harder is to go over RDT 2.0's finite state machine. All right. Now, try to be a bit patient here. Let's focus on the sender side of the FSM first. This time, we do have two states. One is wait for call from above. Oh, okay, this one is familiar, right? So this is the initial state. The sender is waiting for the application process to send data down to the transport layer. Okay, so wait for call from above. And there's going to be a transition triggered by this event, RDT send, the application calling and having data to send. The sender here, transport layer, will then create packets from data. And this time, in order to detect error, we need to add the checksum. So, hey, this is very abstract, but you get the idea. When you're generating the packet, we do need the data from the application layer, but we also need to compute the checksum. All right, so when we generate the segment, make sure that the checksum is somewhere in the header. Very good. So send packet is finally generated. So this is the segment. And sending side of the transport layer service calls UDT send to send the segment out through the underlying channel, right? And that also take the sender from the wait for call from above state to the what? Wait for ACK or next state. Oh yeah, so after we send the data out, then we'll be waiting for feedback from the receiver. Good, makes sense. All right. Now, hey, here, what's coming back as feedback could be positive and negative. So therefore, you see two transitions possible, one over here and the other over here. So this is the negative feedback case, and this is the positive feedback case. Now, the easier one is if the feedback coming back is positive, right? So this is when the sender receives a message back from the network layer, so it needs to be triggered by call from below, RDT receive, the receive packet. And you check whether the receive packet is positive. So if both conditions true, then hey, do nothing. So this is empty set, do nothing, and then return to wait for call from above state. Meaning, hey, positive feedback, so move on with the lecture, for example, so to speak. Right? So, hey, Polly can actually teach more next. But if the feedback is negative, so if some of you say, hey, wait, no, not clear. Can you do this again? Can you talk about it again? Well, in that case, okay, RDT receive, called, and the feedback is negative, what? Yeah, Polly resend the packet. So UDT send, the packet that's generated being sent already once will be, sent once again. Okay, so it's a retransmission. Now, what's a bit interesting is this. When we're at the wait for ACK next state, when we receive a negative feedback, we actually come back here again to wait for feedback. So hopefully the next one is going to be acknowledgement, and therefore we can leave the waiting for feedback state, right? So that was sender side of RDT 2.0, the finite state machine. Now let's move to the receiver side. All right. Whew. There's only one state, cool. But there are two different transitions, one above, the other below. So they are both triggered by RDT receive. So receiver there would be, call from below, from the network layer, saying that network layer, I'm here and I got the segment for you. I got a datagram for you. All right. And then you grab the datagram, remove the IP header, and you see the segment. You try to do the checksum computation, isn't it? Right? And there are two different conditions. One is if the packet does have bit error, meaning the packet is corrupted, then you need to do what? Send the negative feedback. So UDT send. So UDT send is what? To send the data down to the network layer. And so receiver there sending the data down to the network layer. Network layer is going to send it back to the sender. So UDT send NAC is the action being triggered. And receiver comes back to wait for call from below. So it could be a correct data packet. It could be a incorrect data packet, depending on which is the case. So incorrect calls this arc. Correct calls this arc. If it's not corrupted, extract the packet. Okay, extract the data out of the packet, deliver the data up to the receiving process, okay, and then send back positive acknowledgement. All right. So sending feedback. But if everything is correct, the receiving part of the transport layer, receiving part of RDT 2.0 is yet to extract data and pass it further up to the application layer. Okay, now let's walk through a couple examples to show you how the sending side and the receiving side of RDT interacts. Okay, so this is RDT 2.0. And this is an example showing that, hey, there's no bit error in the packets. So, originally, okay, the sender starts from the initial state, wait for call from above. Receiver here also, starting here, wait for call from below. All right, so now we get a call from above. Okay, RDT send being called from the application layer, the sending process. Now, sender side would actually take the data, add the checksum, and create a packet, send packet, and then call the UDT send to send it out. All right, so go through that, and that packet is going to arrive at the receiver end. Receiver side of RDT 2.0 will be called. But there's no error. Okay, so this is the no error case. So it's going to pass this condition, receiving a packet from below and it's not corrupted, therefore triggering these actions being taken. Data extracted out of the receive packet, delivered to the receiving process, and send back in positive acknowledgement. So let me remove the notes. So we'll be triggering this transition and all these actions, and that message is going to come back here. Okay, so you see it flashes, but essentially we were waiting here, right? And that packet, egg packet, is true. Therefore, both together is true, and we do nothing and simply return to wait for a call from above. So this is the case between the interactions of the sender, RDT 2.0, and the receiver, RDT 2.0. Okay, let's do it again. Oops. Okay. At the beginning, here, starting state, here. Sender gets called from above, triggering these actions, taking a transition. And message is going to reach receiver here. Okay, and it matches this condition. Therefore, these are going to be triggered and we stay in the wait for call from below state. And this is going to generate a message being sent back this way. Yeah, and because it's an ACK, therefore we trigger this transition and the sender goes back to wait for call from above state. All right, so this is the no error example. The next example is more interesting, where there is error. All right, so similarly, sender starting from wait for call from above state, receiver starts from the wait for call from below state. And yeah, there's a call coming in, okay, generating the packet, send the packet out through the network layer. Straightforward. So this event match and these actions taken, and we take the transition and move to the wait for ACK or NACK state. And that's going to generate a packet to the receiver. And this time, yeah, this event is triggered. Network layer says I have a packet for you. And which of the condition matches? Well, we have error here this time, so it's corrupt. Therefore, we trigger this transition to occur. Condition match and this action, and then stay in the same state. So we'll be calling UDT send, and we are sending a negative feedback, the NACK. That's gonna fly back. So sender here waiting in the ACK, waiting for ACK or NACK state, then gets a call from below, and it's checking and finds that it's a NACK, not the ACK. Therefore, this transition matches and being triggered. This action is being taken. So UDT send packet is what? Retransmission of the send packet generated earlier. Okay, and sender here stay in the wait for ACK or NACK state. So this is taken and packets being sent again. But the second time, yeah, we're lucky. Second time it's not corrupted, therefore we trigger this transition and another packet being sent back. And this transition now, because of the condition being matching, yeah, we do nothing and we return. The sender returns to wait for call from above state. All right, should we do it again? Probably not, right? You get the idea. Okay, so the interaction between the sending and the receiving machines of RDT 2.0, how they interact. Okay, so there are actions being triggered, and in the meantime, packets being generated, and they would go to the other end, and feedback being generated, coming back to the other end. All right, fun, isn't it? Actually, there's more technical content coming up, so RDT 2.1 is going to be even more complicated. It's a good thing that you guys stay focused and watch through the videos. There's a very good question in the middle of the video playing. That was from Kevin. Yeah. So Kevin was asking, what if the data bits are all okay, but the checksum is corrupted? Well, in that case, if you recall back in UDP packet, yeah, in the UDP packet, the header part has a checksum. So that is a result of computing the entire packet. And see, at the receiver side, if the entire packet is computed again, use the complement, one's complement sum. If the checksum header there does not match the entire packet's checksum, that means there is a mismatch. Okay, and we'll consider the packet corrupted and drop it. So if the data bits are okay, but checksum is bad, that is an unfortunate case because it would not pass the checksum at the receiver. Therefore, we'll have to drop the packet. It's a bit unfortunate, but that's the way it is. And I think Xingci here is also asking, how do you do checksum at the receiver side? Yeah, in TCP or in RDT here, doing the checksum is just like what we do in UDP. So this checksumming functionality is actually the same in UDP as well as in TCP. The difference between UDP and TCP is more. When UDP discover there's bit error either in checksum or data, the packet is dropped. There's no retransmission at all. But in TCP or in RDT, the principle of TCP is reliable data transfer. There's going to be a negative acknowledgement coming back from the receiver to sender, and sender retransmits. All right. And what we did in PA is to send the file size to check, for the receiver to check whether the file size is okay. If you think a little bit about it, a little bit more about it, what we are doing there for PA is not exactly as accurate as checksum did, because there could be bits being flipped and the packet size will still be the same. So the file size check, it works well to check whether the full file has arrived. Okay, it's a form of checksum, but it's not quite the checksum for the content bit check. Okay, content bit integrity check. All right, so it's a very good question from Xingci. File size serve a similar purpose, but it's not quite the same as the regular packet checksum. All right. So now let's move on to RDT 2.1. It looks like some of you guys are liking these RDTs more. Okay, that's a good thing. But RDT 2.0 has a fatal flaw. Yeah. If data can be corrupted, therefore a receiver needs to send ACK and NACK to provide feedback to the sender. The ACK and NACK coming from the receiver to the sender, those packets can also be corrupted. So what if that feedback packet is corrupted? Then the sender will not know whether it's really an ACK or a NACK. So, so should the sender retransmit, or should the sender say, okay, I'm just gonna wait for another call from above? Dilemma. So what do we do with this? If you think a little bit further or recall back, didn't we have the same situation, right? So when data is corrupted, we ask the other end to send feedback. So perhaps we could ask the sender of the data to send feedback so that the receiver will know whether the ACK or NACK is corrupted, therefore retransmit the ACK or retransmit the NACK. Yeah. So how did we deal with the corrupted data? We do the checksum, right? At the receiver. Well, actually, we do the checksum at the sender, adding that into the packet, and receiver check it again. Now, if it's not a match, we send NACK. If it's a match, we send ACK. So this is receiver side action. And therefore, at the sender side, we could retransmit data. So perhaps we'll do this, right? So ACK, NACK corrupted. There's potential. So why don't we do checksum, okay, on the ACK, NACK? So receiver there adds checksum for the ACK, NACK. Sender there checks if the checksum matches. And sender, upon seeing a mismatch, sends a NACK for the ACK or NACK. If it's a match, sends an ACK for the ACK or NACK. Therefore, data receiver there can retransmit the ACK and NACK. Oh, makes sense. But if you think a little bit further, how do we ensure that the ACK NACK for the ACK NACK is going to arrive back at the receiver, right? What if these guys are corrupted and therefore the receiver will not be able to tell whether the former ACK NACK being sent is corrupted or not? Exactly. What happens if the ACK NACK of the ACK NACK gets corrupted? Okay, so you have circular dependency there, and the problem never gets solved. So alternative thinking coming next. The new thinking to address the circular dependency we saw earlier is this. The sender, okay, will just not figure it out, okay, whether it's ACK or NACK being corrupted, okay. So sender will just pretend to be dumb and not trying to ask for a clear answer. Sender here instead retransmit the data that's already sent to the receiver. Would that work? If the corrupted ACK is a NAC, then hey, this addressed the issue, isn't it? If the corrupted feedback is an ACT, then this actually creates duplicates. So the receiver side, in case it being an ACK feedback being corrupted, might have duplicate data. So this is actually not good because at the receiver side, it's going to receive segments one after another. And it's just going to reassemble everything and then pass it up to the receiving process. If that's the case, you might see typos, duplicated sentences, duplicated phrases here, there in the document, or sometimes duplicated pictures or partial pictures. Okay. So in RDT 2.1, to really seriously addressing the issue, we need to add a sequence number to the packet sent so that the receiver side can check the sequence number and see if the packet that has already been received earlier matches the sequence number that I'm receiving now, the receiver is receiving now. If they match, then that is very likely a duplicate from the sender, okay? And the corrupted feedback is an ACK. Okay. So, entirely in RDT 2.0, sender will just retransmit the current packet in case the feedback is corrupted. But in the packet, it's going to carry a sequence number that will allow the receiver to tell whether this is a duplicate or not. In case the receiver detects it's a duplicate, it would scar the duplicated packet. And this is RDT 2.1. And there's one more thing we need to talk about. That tells a little bit about the sequence number requirement here. Think a little bit more. RDT 2.0, RDT 2.1. The sender behaves this way. After sending one data packet, it's going to stop and wait for feedback until everything is cleared. Then it will go back to send data again. So sender sends one packet and it's going to wait for feedback until everything is cleared and move on. So you see, if the receiver during the phase in stop and wait state receiving two packets carrying the same sequence number, then that must be a duplicate due to a corrupted ACK, isn't it? Yeah, so sequence number in such form of reliable data transfer is very simple. It needs only one bit, two numbers, 0 and 1, to tell whether it's a duplicate apart from a new packet. Now, judging from the description, it sounded somewhat easy, not that complicated. But if we look at the finite state machine, it looks somewhat complicated. And you know what? This is only the sender side of the FSM. We have not yet looked at the receiver side, all right? So this is the sender side of RDT 2.1, which is the version of reliable data transfer that handles corrupted ACK-NACs coming back from the receiver. Now, the easiest way to look at the finite state machine here is by drawing a line separating the two mirror parts. So if you look at the upper right part of it, this looks like the wait for call from above state in RDT 2.0 sender, isn't it? And wait for ACK and NAC, this looks like the waiting for feedback state in RDT 2.0 sender. If you go down further, this other half, it's actually very similar. Wait for call from above, and then wait for ACK-NAC. Okay, the only difference is this. Wait for call for packet 0 from above versus wait for call for packet 1 from above. We just talked about the sequence number required to separate two packets one after another from a duplicate, a retransmission of an existing packet, isn't it? So having 0 and 1 is a way to tell duplicate packet apart from a new, a fresh packet. So we do need to have the separation here in RDT 2.1 sender. And as a result, when we get a call from above, so application calls RDT send data, will then trigger these actions to occur. So we'll be making packets, taking data, and we do the checksum, right? So this is in order for the receiver to check and see if the receiver sends ACK or NACK. The new thing we add here is, to add sequence number to the packet we're creating. So the send packet here now contains not just data, not just checksum, but also a sequence number. And as usual, we send it out through the network layer. So we call at the transport layer called UDT send. Now, the second thing that is a bit unusual is also this. Hey, the feedback state, wait for feedback state, you see, wow, the condition looks all complicated. Particularly if you see, we're now checking first whether the feedback we receive is corrupted or not, whether it's actually intact or not. So this is the case when it's corrupted. This is the case when it's not corrupted. So if we receive a packet from the network layer, receive a feedback packet from the network layer, and we check that it's not corrupted, everything is fine. And that packet is a positive feedback. That means what? Transmission of packet 0, perfect. So we do nothing and then we move on to wait for call from above again. All right. So this transition here is straightforward. Now, what is a little bit unstraightforward is this transition. So this is the transition that we come back to wait for feedback again. Okay, so these are the complicated cases. You see here, if the ACK or NACK coming back is corrupted, what do we do in RDT 2.1? We'll just retransmit the packet that's sent once earlier, isn't it? So if it's corrupted, simply send it again. So the send packet here is not actually being reassigned. So it will be the packet we have sent earlier. So it will be carrying sequence number 0. There's another condition. If the packet is not corrupted, but it is a negative acknowledgement, then it's just like in RDT 2.0, we retransmit. All right, so this transition here gets, doubled. It's checking two conditions. If it's not corrupted, a negative acknowledgement, retransmit. If it's corrupted, also retransmit. So we have two conditions that actually ended up doing the same thing, just retransmit. All right. And so that is the sender side of RDT 2.1, and we'll just not cover the rest of it because it's pretty much the mirror. Okay, the only difference is just that handling data packet 0 versus data packet 1. All right, so that was RDT 2.1, the sender side. The receiver side is coming up after the break. And here we do have another question, which is asking, how do we check whether NACK or ACK is corrupted? So you see already, after I described the full finite state machine, that there seems to be something coming back with the ACK-NACK so that we could check whether the ACK-NACK is corrupted. Now, the checksum being attached to the ACK-NACK, that is in the receiver part of the RDT 2.1, which is coming up in the next hour. So be a bit patient, Kevin. It's coming ahead. Now, what I want to do is to draw your attention to the midterm exam. Yeah, so if you go to the Facebook group, you should see a post from Polly yesterday saying that what is going to be the exact time the exam will take place. So that's going to be next Thursday, okay, starting 10:20 to 12:10. You might want to arrive a little bit earlier so that you can tune in and allow us to do the ID check and stuff, okay? There will be also lecture next Wednesday, okay, although it's only 50 minutes, because by the end of today, there's going to be a part in the chapter 3.4.1 that we will not be able to cover. So next Wednesday, during this hour here, we're going to cover the rest of the 341 there so that you get the full picture. So the exam scope is going to be the entire chapter 1, excluding the history section, the entire chapter 2. But for the circuit programming part, you might be tested, okay, the circuit programming skill, but it's going to be the Golan circuit programming skill. And then for chapter 3, it's going to cover all the way from the overview to UDP to TCP or RDT 1.0, 2.0, 2.1 as you heard now. By the end of today, 2.2, and next Wednesday, 3.0. So there are actually quite a few versions and subversions of these RDTs you need to go through. So the scope of the midterm exam is going to be to the end of these RDTs. And number 3 here. Okay. So if you're wondering what the exam questions are going to be like, you can go back to the old exams, which I actually point you guys to already yesterday. Okay. So maybe download a couple of them and try to work on it a little bit, and then you get a feel of the style that Polly is asking questions. Now, there'll be a couple major differences for the midterm exam this year because we're going all online. And many thanks for your patience for the change of the format. So the way we'll be running the exam is this. Okay, the exam is going to be a Google form. All right. So if you click into this link that I'm providing, it should take you to a Google form. Okay. So that is where you're gonna do your exam. Okay. So you will be inputting your email address. By the way, you need to log in using your Gmail account. So the email collection is going to be automatic. But make sure that you state your name. It can be your English name or your Chinese name. So either way. Student ID, however, is going to be unique. So fill those in. Okay, so I'm just going to do a test. Okay, so let me use my Gmail. What is your name? Let's see. Polly Huang. And my ID. Well, let me just borrow one of you guys' ID. Okay, how about that? So I just made it up. All right, so that takes you in. Okay, so those are required field. Once you're in, then you get to explore. Oh, what is problem 1? Read it through. Consider a micro internet consisting of 5 subnets, X, Y, V, W, and Z. Problem 1.1, so 1-1 is asking which of the subnets is classified as an institutional network in the lecture. Oh, okay. So you have to, think a little bit, recall a little bit. What is an institutional network? And what is a residential network? And what is a mobile network? Okay, so which one looks more like a mobile network? X, Y, Z, W, V. Okay. And so you provide your answer down here. Let's say, yeah, it looks more like it should be X here. So you can leave it blank if you are not quite sure, and you can also come back to work on an earlier problem. Okay. Problem 2 is shorter. Based on your understanding of packet switching and circuit switching principle, select the keywords that fit better the characteristics of a circuit switching network. So yeah, circuit switching, idle resource, no contention, no congestion, reservation. It should be a multiple choice. Okay, so I need to change the test form here to allow multiple choices for this question. Say call setup, reservation, idle resource. I think delay guarantee as well should all be keywords associated with the circuit switching network. So you can move on and try more questions out. But these problems are actually from previous years, so they are not going to be the questions for the problem set for the midterm this year. Okay, so this is just so that you get the feel of how it's like filling up Google form for the exams. All right. So let's go back and back. Oh wait, yeah, it's here. Another major difference is that you guys will need to join the Google Meet video conference session. So by clicking in here, so give me a second, I just disabled it because it's consuming the network bandwidth I'm using to do the streaming. I think that's why I had a bit of trouble with the OBS earlier, because OBS is actually buffering the videos it's actually generating because the network is not working well. Now, because the buffering is not controlled very well in OBS, and it occupies pretty much the entire memory space I have on my Mac, and therefore OBS actually kicks itself out, and that's usually the problem there. Let me see if I can go back to the meeting room here. Okay, it doesn't work anymore. So let me start another one, okay, and let you know what is the code here. Okay, so go and enjoy the break, which is now only 7 minutes. And then I'll be posting the new link to the Google Meet. So come and join the Google Meet session when you're back from your bathroom break. So I'm just going to post it here. Okay, I'm going to post it in the comment below. Okay, so join the session. And you can see whether your video camera is working or whether your network capacity is going to be sufficient. Okay. Going through the exam. All right. Oh, and good news is that, yeah, the exam is going to be open book, open internet, so you don't have to memorize all that much. You just need to get yourself familiar, okay, with all these notions that we've talked about. So open book, open internet. You can be a bit more secure. So it will be more like a competition with time, okay, for the midterm exam. All right, so during the Google Meet, especially at the beginning, I need you to hold your ID up so I see the picture on your ID and your face as well. So holding the picture and showing. So let me just go back here. So I need you to hold your ID and showing your face like this. Oh, there's one trying. Okay, good. And so I see you at the beginning. But afterwards, you can just go back and focus on your exam. Okay, so feel free to look down. Just that, hey, hi. Oh, there's another student in. Okay, 新词. So yeah, good. So that's about it. Let's go now, take a break, and we'll come back in now only 4 minutes. Okay, and I have to go to the bathroom. Okay, if there are other questions, then I'll try to come back and address them later. Okay, so once you've tried and it seems to be working, then you're fine to go. Okay. Okay, there you go. And you are eta. Okay, good. Very good. So yeah, a number of you have already tested out, then you're good. Yeah. So essentially, the midterm exam is just gonna be the Google Meet session and you working on the Google form. There's not gonna be a YouTube live stream, all right? So, okay, there you go. That's 邵家子, all right? Good. Okay, good. So it seems to be working well. Okay. And that's Jiting. Okay, good. Working well. Hey. So some of you guys, for the first time I see, yeah. Okay, I never really see you guys' face. Okay, good. And this is Kai Jun. All right. Okay, seems to be working. Very good. All right, so let's now come back to the second hour. Okay, so there might be more of you trying things out, so feel free. Let's see. Rocket has a question. What is the frequency of packet corruption on the internet? Oh, wow. Are we looking at something closer to or even greater? The chance is very low that the packet get corrupted. Very, very low. I think it's even lower than 0.05%. But the thing is that there are so many packets, so many bits we're generating. So actually, the frequency, so if you ask about the time, okay, how often the checksum fail, then it's surprisingly frequent. I forgot the exact number. I can look it up for you, but it's actually surprisingly frequent. It could be like days or within a week, then you see a checksum fail, meaning the checksum pass, but the bits in the data or in the checksum might be errors. Okay, some of you who might be wondering whether checksum is really working, because you have actually way more than 16 bits of data there. Okay, and checksum is only 16 bits. So you're taking the summary of all the data and see if they match. Okay, so there's a slight chance that the data might be slightly different, but they ended up having the same checksum, right? So it's a many-to-one mapping function there, essentially. The ones complement sum. So there is a certain chance some of these data bits gets mapped to the same checksum. So if the flipping is such that, hey, it happens to be one of these data bits such that it maps to the same checksum, then you fail. Okay, so yeah, there's a slight chance. Okay, Rocket, you're right. That packets slipped through. Okay, and checksum did not catch all the corrupted packets. Haoyu, if sudden internet disconnection, do we have additional time to re-answer? What we write before may lose. Yes, that's a very good question. You see here that at the end of completing the Google form, you can always submit and then come back to work on it and then submit again. So if you have a sudden disconnection, but come back real quick, then you should be safe. However, if your disconnection goes a bit longer, then you will have trouble typing things up as well, as the exam is going to be also a competition with time. So make sure you go somewhere the internet connectivity is really good. All right. So for example, if you are in the dorm, then you should be safe. If you are very insecure, try to use one of the major machines in the computing centers, in the computer labs. Okay, I think there are these workstation rooms, but I don't know exactly how they are maintained. Okay, or take your laptop to somewhere the Wi-Fi connectivity is good. Okay, so go somewhere there are not many people. That way the Wi-Fi connectivity will be better, because when you are around a lot of people, then they might all be competing for the Wi-Fi access. Nowadays, there are quite of us doing the lecturing online, so chances also high that they are also tuning in to some lectures or also having an exam. Okay, so go definitely find somewhere the internet is good and reliable. So did I mention something like that? Yeah, internet connectivity. Okay, you need the working camera and good stable internet connectivity. All right. If it's only very short outage, you'll be okay. Yeah, so Pei An is calling in. All right. So give it a try and see if you can see me and I get to see you. Make sure that your camera is working. Okay, good. So yeah, the receiver part of RDT 2.1. And this is the receiver of RDT 2.1. You see, similarly, the number of states and transitions also doubled. We borrow the technique I used to describe the sender side. So the line in the middle here actually indicates the upper left and the lower right.
Right.
They are the mirror of each other. The difference is just
Still working.
that the upper left is handling data sequence number 0, expecting data sequence number 0. And the lower right expecting and handling sequence number 1. And then we propose that we walk through the state machine this way. First, assuming that there are not going to be any data corruptions nor the ACNAC corruptions, meaning things are going perfectly. At the beginning, receiver will start from the initial state, wait for packet 0 coming from below. And nothing's going to be wrong there, therefore it will be triggering, this condition, this transition. Okay, so receiving a packet, no corruption, and it's carrying sequence number 0 here. Okay, expecting 0, carrying sequence number 0, perfect. Let's extract the data, pass it up to the application layer, generate the add packet, but this time what? Including the checksum. So this is coded in RDT 2.1 because we are now assuming also ACNAC could be corrupted. So checksum here is to enable the data center to be able to check whether the add packet or the NAC packet is corrupted. So that ACK packet with the checksum will be generated and sent back. All right, straightforward. And we move to the new state, wait for 0 from below. Similarly, we'll be getting a packet from below, receive RDT, and not corrupted, and carrying the expected sequence number 1. Cool, happy again. Extract data out of the packet, pass it up to the application layer, generating an ACK with checksum, send it back. Upon finishing all these actions, we take the transition. Receiver here, go back to wait for 0 from below. If another packet comes in, not corrupted, carrying sequence number 0, again happy, take the transition, wait for 1 below. And this will go on and on and on and on and on. And when there's no data corruption, when there's no ACNAC corruption. Now, what if there's data corruption in RDT 2.0 Yeah, that's where we begin to see these transitions showing in the receiver side of RDT 2.0. This is the case when we are expecting 1, but we get the corrupted data. Then we say, hey, the data is corrupted. Generate a negative acknowledgement, but hey, in RDT 2.1, we do need to include the checksum and send it back to the data center. Similarly here, if we're expecting 0, receiving a packet, it's corrupted. Generate the neg, send it back to the data center. Okay, so these two transitions we know well. Okay, they have already appeared in RDT 2.0. The two transitions remaining, yeah, this one and this one here. So this guy and this guy here. Okay. Just like these two, very similar. These two, very similar. They are actually very similar as well. So let's focus on this guy here. So this is the case when we are waiting for packet 0 to arrive. We did get a packet, it's not corrupted, but wrong sequence number. How can this be happening? Well, then this must be because, hey, sequence 1 here has already been received earlier. That's why we've already moved on to wait for 0. Now, receiver here, receiving 1, will be also sending an ACK back to the data center. But the data center there finds that packet corrupted. Okay? That's when the sender retransmit sequence 1, thinking, I'm not sure, I'll just retransmit. And therefore, we get a duplicate packet here. Right? So if that's a duplicate, no. That's not extract packet, that's not deliver, again, the same thing up to the application layer. So you see here, the only actions we'll be taking is just not extracting data, not passing up to the application layer, but only to generate the acknowledgement and send it back to the sender. Now, is it necessary to generate another ACK? It is, isn't it? Because the previous ACK here, yeah, it was corrupted. So sender there is just gonna think that data might not be there. Data might not be there. To be safe, let's just retransmit. So this ACK here is actually crucial, so that the sender, hopefully the second time, gets the ACK all right and they can move on to what? Wait for call from above for packet 0, because it's now stuck at the packet 1's feedback. So, yeah, this is RDT 2.1. Now let's use a couple of very simple scenarios to demonstrate how the sender and the receiver interact. So this is RDT 2.1, no error case, and the scenario is simply first to send 1 packet, and then second, continue and send yet another packet. So our goal is to find out all the transitions being triggered until it reaches the steady state. Now, in order to find out what transitions each of these finite state machines will be taking, we need to know the starting state. Now, at the beginning of the sender, it's going to start from the initial state. So the starting state will be the initial state for the first transition. Similarly for the receiver, this is the initial state. Therefore, the starting state of the first transition at the receiver side is going to be also the initial state. Now, event is the send 1 packet. Now, we're here at the starting state to determine what transitions to take. Let's check out what the transitions are. Well, starting from this state, there's only one possibility, which is T1. And it happens to be what? Getting a call from above, which is to send 1 packet. So, obviously, the first transition we'll be taking is at the sender side, and it's T1. And it matches this event here, and it's going to complete all the actions listed here, which is to generate data packet 0 and send it out. At this point, sender here enters the wait for ACK or NAC 0 state, right? So very important, before you determine what transition to take next, what is the starting state right now? What are the possibilities? Are there multiple transitions one can take from the starting state? If there are, be careful. What is the triggering event? Okay, so pick the transition that's matching the triggering event. And then take the actions, and then finish the transition, and land on the ending state. All right, so let me repeat. Starting state, possible transitions, match the triggering event, and then land on the ending state. So now we're done with T1. So the result of T1 is there's a packet being generated, isn't it? And that's going to arrive at the receiver side. Receiver side currently here. So this is going to be the starting state of the next transition being triggered. And it's receiving a packet from below. So let's see, what are the possible transitions? 1, 2, 3, because all 3 of them starts from the state here. Now, event is, yeah, we receive a packet, definitely. Okay. So all transitions is triggered by receiving a packet. But exactly which one is triggered depends on checking whether the packet is corrupted or not. And we're assuming no errors, so this one is not possible. So this one passed to this point, this one passed to this point. But there's one more check. Is the packet sequence number 0 or sequence number 1? Here, we are generating sequence number 0. Therefore, eventually this transition wins. And so we'll be taking T11 over here and taking all these actions and moving the receiver to this state, wait for 1 from below. And now next, right over here, the receiver is generating an ACK packet and it's being sent back. So that's gonna trigger an ACK packet arriving back at the sender. So sender here currently at the wait for ACK or NAC 0 state. See, there are 2 possible transitions. So which of these matches the ACK packet with no error? Yeah, this one here. No error, and it's ACK packet. So we'll be taking T2 and finish all the action here, which is doing nothing, and enter the wait for call 1 from above state. So sender here goes to this state. And there's nothing to be done here. No more packet being generated flying back to the receiver, so we could have stabilized this right here. So sender here, stop here. Receiver, stop here. Okay? And in the process, we take 3 transitions. First one is T1 at the sender side. Second is what? T11 at the receiver side. And the third being T2 at the sender side. And now let's move on with scenario 2. So we'll continue from S1. Well, we actually finish S1 here and here for respectively the sender and receiver. Now we'll be sending yet another packet. So sender here gets call from above, RDT send. Therefore, these actions will be taken and we'll follow through T3, that transition, and enter the wait for ACK NAC 1 state. Now this is going to generate packet data 1, and this is going to go to the receiver, which is sitting right here, wait for 1 from below. There are 3 possible transitions stemming from the state here. And which one does our receiver take? Well, receive, 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 and this is packet 1 not corrupted, so not corrupted, not corrupted. So this one is quickly out, and it's packet 1, so yeah, this one here wins. Therefore, we take T12, take all these actions and go to the wait for 0 from below state here for the receiver. Now an ACK packet will be generated, and this is going to go back to the receiver, which is currently waiting for ACK or NACK 1. And it's getting an ACK for 1. It's going to do nothing but follow through T4 and enter the wait for call 0 from above. So overall, sender here takes T3, generates data, therefore calls T12 at the receiver side, generates ACK, and therefore calls T4 at the sender. And finally, both of them stabilizes, because of no action here in the last transition, and sender goes back to wait for call from above, receiver goes back to wait for 0 from below. Now, this slide is called discussion, but what it does is really the summary of 2.1. So at the sender side, what's being special is this. Sender checks whether the ACK/NACK is corrupted. Okay. Now, in order to prevent having duplicate packets, the sender side now also assign a sequence number to the data packet sent. So it's either 0 or 1. And in order to track data packets carrying the sequence number, there are now twice the amount of states and twice the amount of the transitions. So the states somehow need to remember what is the expected sequence number. Receiver side, the primary function is to avoid receiving duplicate packets. So it would check the sequence number, whether it's a repeating sequence number. In that case, the packet is a duplicate. Okay. If that is the case, the data will not be extracted passed up to the application. It's just going to be discarded. But be careful. Receiver here seeing a duplicate, although not extracting data, not passing it up to the application, it will still what? Send an ACK out again. All right. Why? Because the former ACK or NACK being sent back to the sender. Only the sender knows whether the packet is corrupted. And if it's corrupted, the sender doesn't even know whether it's an ACK or NACK. So sender there is trying to be fuzzy and do the best thing that he can do, which is to repeat sending the data that has been previously sent. So receiver here needs to be more considerate. In case it's a duplicate packet, send back the ACK again, just in case it's an ACK packet being sent back and it's corrupted at the sender. Now at least the sender will be informed. Everything is okay and move on. And we move on as well to quiz number 12. Okay, so we actually went through a couple very simple examples assuming no errors. So how about we try some scenarios with errors? Okay, so this is scenario number 3. So if you look at the bottom, show the FSM transition triggered in sequence. In scenario 3, we send one packet, but there's a bit error in the packet that we send. And then assume there will be no more bit errors afterwards. Not in the data, not in the ACK or NACK. So now, what are the transitions being triggered in sequence? Think about this. So this is a very important quiz. I'm going to give you more time this time. Let's do this. And you have 5 minutes. Set the timer for 5 minutes. Okay, wow, so we do have one team managing to figure it out in 5 minutes. Okay, that is really cool. So that was Kevin, I think team 4, yeah. So yeah, Polly also worked on it a little bit, and Polly is also getting T1, T15, T5, T11, and T2. Okay, Bingjia, team 5 there, have T3, T13, T6, T12, and T4. Interesting. Yeah, okay, so if Bingjia starting from the call from above 1, yeah, then you have the right sequence of transitions, definitely. Yes. Okay. All right, so Darius, team 12 there. Yeah, also have T1, T15, T5, T11, and T2. Starting from 1 state. There you go. So I guess Jiazi and Bingjia are both team 5. Yes, yes. So yeah, I saw the Bingjia sensor and I kind of figured it out. Yeah, so you guys started from the wait for call from above, packet 1. So you are kind of doing what S2, the scenario 2 is S2 to continue from scenario 1. Yeah, that's also fine. So you guys got it. All right, very good. So for those of you who might be struggling a little bit, because the next quiz is still about RDT 2.1 with errors. Okay, let me go through. Yeah, Team 2 also come up with the solution. All right. So let me go through the solution for quiz 12 so that hopefully things are a little bit clearer for you and so that it's easier for you to work on quiz 13. Okay, so this is an abstract system, so it takes time to exercise. Okay, so let me exercise the process here. Okay, so the thinking process, yeah, you guys provided correct answer, but you did not provide the thinking process. So to help those who are still thinking about this, let me show Polly's thinking process here. All right. So let's assume we start from wait for call 0 from above at the sender side and wait for 0 from below at the receiver side. Okay. And so scenario 3 says that's send 1 packet, okay, but there is a bit error. So if we are starting from this state here, send 1 packet. Well, there's only one transition from wait for call 0 from above, which is this one here. And this is indeed getting a call from above to send data. So we generate 0 and send it out. Okay, so triggering T1. And this packet is going to go to what? The receiver side. Okay, now things are a little bit complicated here because we do have 3 different transitions. Okay, in the wait for 0 from below state, right? So T11, T15, and T16 are all possible. So our assumption is that there is a bit error, okay, in the data packet. So no corrupt, so these 2 will be ruled out. And the only one that's matching is transition 15. So we take T15 and finish all the action, which is generating a negative acknowledgement and send the negative acknowledgement back. And the transition says that we need to come back here and stay in the wait for 0 from below state. Okay. So, yeah. The number 1 transition being triggered is there, T1. Okay, and we move to the wait for ACK or NAC 0 state. Okay, and that is going to trigger T5, indicated here. So triggering T5 being the second transition being fired. And this NAC will go back, right, to the sender. There are 2 transitions to consider now. Okay, and it's a NAC, so it's going to match this triggering event and therefore retransmit the packet. So you see, moving from transition number 2 to this guy here. So this is going to trigger transition 3, which is T5. And T5's data packet is come back. It's going to come back to the receiver. Okay. And this time, yeah, no more bit errors. Therefore, it should be one of these two conditions. And it's carrying what? Sequence number 0. Therefore, it should match this triggering condition, therefore triggering T11. So the animation should go like this, right? Going to T11. And T11 there is the forced transition. Now this app packet is going to come back to the receiver again, while the receiver moves to the wait for 1 from below state. And this is going to match this condition, triggering T2 to fire, and we move from wait for ACNAC 0 to the wait for call 1 from above state. And because we're doing nothing here, so the entire machine stabilizes. So RDT 2.1 finally sits still and remains static until there's another event coming. All right. So T1, T15, T5, and then T11, finally T2. Okay. If we're starting from this state, that is the correct sequence. I hope that it's more clear now. And let's see if quiz 13 is slightly easier. All right. So team 2 also get it right. Team 1 also get it right. Okay, so team 2's team members correcting for the team members. All right, that's good. Very good teamwork there. So S4 here is a little bit tricky. Let's continue from S3, meaning, hey, where are we at the end of S3? So we are now in the wait for call 1 from above state at the sender side, right? And we are at the wait for 1 from below for the receiver side. Good. Now, send one more packet, but there's a bit error in the returned NAC. Oh. If the receiver is going to send the NAC back, that means, yeah, the data packet is corrupted. And the NAC packet is going to have a bit error as well. Okay, so the sequence is a little bit different, isn't it, this time? Okay, so exercise it again. And you have also 5 minutes to work on this. Set the timer for 5 minutes. Oh, okay. Yeah, Team 5 is also collaborating with the team members, okay, helping clarify. Sure. Right. Oh wow, that's fast. Polly hasn't finished her. Wait. Uh-huh. Oh wow, all right. Team 12. Oh, that is perfect. Very good. Team 3 got it as well. Oh, I mean, Team 5 got it. 4 also. Very good. So you see, once you get yourself familiar with the system, it's not exactly that complicated. It's just that it looks complicated. And the easiest way to think is probably to not think too much and pretend that you are one of these machines and following the conditions, okay, taking the transitions. Yes. All right, good. All right, so, and let me just walk you through quiz 12. Okay, so the animation that I have generated so that it helps you a little bit further. So we're at the set wait for call 1 from above and wait for call 1 from below state for the sender and receiver correspondingly. Okay, so here and here. Good. And we send the packet again, but it's going to trigger a NAC, which means, yeah, the T3 we're triggering there generates a data packet, and that should go back to the receiver and triggering what? Yeah, the packet is corrupted and sending the NAC. So that's going to go to T13. All right. And that NAC is going to come back to the sender and triggering, yeah, because it's matching the ease NAC condition, right? So that will be transition 3, T6. And a retransmission of the data being sent. And finally, this time, no bit error, as we are assuming here, no more bit errors afterwards. So T12 is the number 4 transition. And that data is going to arrive back to the sender. And everything is okay, therefore triggering T4. And we do nothing and move back to wait for call 0 from above. All right. Good, I see. Okay, team 2 also got it. Very good. And that takes us to the last topics, RDT 2.2. So what RDT does is simply trying to make sure there are less packet formats we need to generate. Currently, we still need to generate ACK packets as well as the NAC packets. RDT 2.2, it's essentially the same as 2.1 except here. It's going to be the NAC-free version of 2.1. By saying that, what I meant is, well, in 2.1, when the packet arrives at the receiver, okay, we send positive acknowledgement, that is ACK. Well, in case that data packet is corrupted, we send a negative acknowledgement, that is NAK. Now, as a result, we do have like 2 packet formats, right? One says I am acknowledgement, the other says I'm negative acknowledgement. So RDT 2.2 here is essentially to say, let's not have 2 different packet formats, just have 1 acknowledgement packet, but adds a bit in the acknowledgement packet, and we change the bit, okay, the value in the bit to indicate whether it's really a positive acknowledgement or a negative acknowledgement, all right? So same functionality as 2.1, but using only ACK packet. But the ACK packet will be carrying an extra bit. That is also the sequence number. Okay, so that is the sequence number bit. Okay, and the value in the sequence number bit is going to tell the sender whether this is a positive acknowledgement or a negative acknowledgement. All right. So now we have, a NAC-free protocol. Receiver sends acknowledgement packet for the last packet received. Okay. Think a little bit about it. So the receiver starting from waiting for call from below 0. Right? So if packet 0 is received okay, receiver here sends acknowledgement for packet 0. Because packet 0 received okay. The last packet received okay is what? Sequence number equals 0. Now, go to wait for call from below, packet 1. So if packet 1 arrives at the receiver and it's corrupted, what does receiver do? Which packet is the last received being okay? Well, 1 is not okay. So, still sending ACK packet, but sequence number bit there is 0 again. All right. But at the sender side, what's going to happen is sender will receive the first ACK with sequence number 0, right? Indicating packet 0 is received okay. But sender there is going to receive another sequence number 0 ACK. Ooh. Hey, how come I get acknowledgement for sequence number 0 twice? Having duplicate acknowledgement at a particular sequence number that indicates the next data packet that sender just sent out was corrupted. A negative acknowledgement in a way. So receiving duplicate is essentially signaling, sender is sending an NAC, right? So sender there will have to what? Retransmit the packet that's last sent. Now let's try to develop RDT 2.2's finite state machines. So here what we will do is to borrow from 2.1 and start from the receiver side of the finite state machine. All right, so initial state is wait for 0 from below. So we're expecting data 0. And we get 1 if it's not corrupted and indeed carrying sequence number 0. Then we extract data, pass it up to the application layer, generate an ACK packet with the checksum, and then send it out. Now, if it's 2.2, we'll be generating an ACK packet, all right, but this ACK packet should be carrying a sequence number, isn't it? And according to 2.2, the sequence number should be the last data packet received okay. And what is the sequence number of the data packet received okay? Well, we just actually received 0. So, you're correct. The ACK packet we're generating here for RDT 2.2 should carry sequence number 0. And so once we finish all the actions, we'll be finishing the transition and move to the next state, wait for 1 from below. And if we get packet 1 coming in, passing these conditions, so indeed carrying sequence number 1 in this data packet, then similarly, we take the data out, generate ACK, and send it out. And here, the ACK sequence number will be what? Data 1, the sequence number that we just received. So as a result, we could actually conclude the receiver side of RDT 2.2 should look more like this. And I'm ignoring the upper right part of the receiver's finite machine. So receiving a packet, not corrupted, carrying sequence number 1. The ACK packet will be generating, of course, it needs to be an ACK packet format carrying checksum. It also carries what? The sequence number of the data we just received, okay, and which is 1 here. So for this other transition at the top, then it will be make packet 0 ACK checksum. Now, hey, the receiver side of RDT 2.1 actually have all these other transitions, right? So we only handle this part and extend it to 2.2. We will still have to extend these transitions so that it will work for 2.2. Now, these are actually exact mirror of each other, so let's just focus on one side. Okay. Now, let's pick this transition first and see if we could evolve it as well into 2.2. So this is receiving a data packet, but it's corrupted. So in 2.1, we send a negative acknowledgement. But for 2.2, we don't send negative acknowledgement packets anymore because we don't have that format. Instead, we send ACK. But we have to carry a specific sequence number to indicate whether this is really a positive acknowledgement or a negative acknowledgement. So, yeah, the rule of thumb generating the sequence number there is what? Who is the last data packet received? Okay. Now, receiver is currently waiting for data 0 coming from below. So what that means is that the last packet received OK should be carrying sequence number 1. So ACK here should give the sequence number of the data packet last received OK. So yep, it should be ACK1 here that we're sending back to the data center. Now, what about this other transition? Receiving a packet, not corrupted, but carrying sequence number 1. This is not the data 0 we're expecting. All right. How can this be happening? Yeah, so this is the very odd situation where the previous data, ACK, being sent back to the sender gets corrupted, if you recall. Yeah, ACK packet or negative acknowledgements can be corrupted now, right, in version 2. Now, if negative acknowledgement is corrupted, sender simply retransmit, no problem. But if positive acknowledgement gets corrupted, sender also retransmit. And that is this situation here. You already sent back an acknowledgement for data 1, and yet it's receiving data 1 again. Yep. So this is the situation. ACK packet gets corrupted, and so you're receiving a duplicate of data 1. So we do not extract data and pass it up to the application because that's going to repeat words, repeat letters, repeat sentences. Okay. So we only send back ACK. And this ACK should be what? Acting the last packet received OK, therefore also carrying sequence number 1. Okay. Now, if you look at this guy and this guy, both transitions, the actions they'll be taking will be identical now, right? Both sending acknowledgement packets carrying sequence number 1. So then perhaps we could just combine the two transitions. Receive a packet from below, checking if it's corrupted, or carrying sequence number 1, send ACK packet 1. Right? And you know what? ACK packet sequence number 1 is already being generated here. Send PKT, if you do not replace this variable's value, it will remain the same. And so if we just simply call this, then yeah, we just combine the two transitions and make it very brief, like this. RDT, either corrupt or carrying sequence number 1, simply send back the send packet that has been generated here, which is an ACK with sequence number 1. And that's all for today. Feel free to go and have lunch. Next Wednesday, we're going to wrap up 2.2 as well as 3.0. And then Thursday, the midterm exam. In the meantime, if you have any questions, feel free to ask. Post it on the Facebook group, or feel free to send me emails or FB messages. I'm going to leave the session on for a little while, so some of the teams maybe join a bit late, can still work on the quizzes. So Q2, Q12, and Q13. All right, so let me just post Q13 there in case you guys are still working on it. Oh, by the way, if you guys want to try the video stuff out, the Google Meet session out, it's okay to do it also now. I'm going to be still here for another 10-20 minutes. Okay, team 7. Good. Yes. Oh, hi.
Am I too early?
It's okay. It's okay. So guys, I'm gonna end the session now. And so that I hold the office hour. Want to end stream? Yes.